Hello and welcome to lecture 4 of Momentum and Impulse in Phys 1101, and here we get to the real point of it all, which is the law of conservation of momentum. So we were looking at this collision between cars in the last lecture, and we found that the impulse imparted by A on B was the negative of the impulse by B on A. And this was just because of Newton's third law. You can really think of this as nothing more than a way of rewriting Newton's third law. Now, in the case that the internal forces, the force of A on B and the force of B on A, are the only forces that matter, so this is what we called an isolated system, this turns into that the change in the momentum of B equals the negative of the change of momentum in A. And note that this is all very general. Newton's third law always applies, and for any isolated system, this is going to result in the momentums obeying this. So this is true for any isolated system. We can rewrite it in a few ways that are often more useful. If I just bring my PA over onto this side, this is saying that the sum of the changes of the momentums are 0. Well, if the sum of the changes are 0, that means the total momentum is staying constant. Or I could rewrite it one more way, and this is usually the most useful way of writing it. The sum of the initial momentums equals the sum of the final momentums. And now look at what's happened here. This is connecting the momentum initially with the momentum finally. So this is a hallmark of laws like this, that they connect early times with later times by telling you something that doesn't change. And so before-after pictures are going to be very useful whenever you're using conservation laws to solve a problem. This, in the various forms I wrote it, is called the law of conservation of momentum. It says that momentum is conserved, or in other words, momentum does not change in isolated systems. And note what this means. This doesn't mean that the individual momentums of the objects don't change. It means that the total momentum of the system doesn't change if the system is isolated. So to see how this works, let's go back to car crashes. Here we have a fairly typical example that would come up in real accident investigations. Let's say we have a car that's running into another car, and this one's parked, right? So it was stationary before the collision. And as accident investigators, we might be quite keenly interested in how fast this car was going before the collision. And from tire tracks, it's often quite easy to figure out how fast the cars were going after the collision, because after the collision, all that's acting is static friction, and we know ways to figure this stuff out. So let's figure out the velocity of car A before the collision. I'm going to set right as positive, and I'm not going to worry about any vector symbols because everything's one-dimensional here. And so I can just use conservation of momentum. We've already seen how this plays out in car crashes. There should be kinetic friction, but it should be small compared to the forces between the cars. And so I can say that the total momentum before is equal to the total momentum after. And I'm going to use primes to stand for after. So let's just write all that out. MA VA, there is the momentum of car A before the collision, plus MB VB, there's the momentum of car B before the collision, is MA VA prime plus MB VB prime. This is the total momentum before equaling the total momentum after. And I have the nice simplification here that VB is 0. And so I just have that VA, which is the thing we're looking for, is just going to be MA VA prime plus MB VB prime all over MA. And so that's pretty easy to plug in. is 11.5 meters per second. Which is probably a little fast for a parking lot, right? Let's look at one more example, and this is going to illustrate some of the vector nature of all of this. So let's say we have a flat car running along on the tracks, and some object, I'm going to call it the load, is dropped onto it. This looks like an accident, right? If the load is dropped on and it's going that fast as it hits probably a cable snapped or something, and this is smashing into the flat car. Anyway, after some probably rather messy collision in which the load bounces around a bit on top of the flat car, they are now going to be moving together to the right at some speed that we would like to know. And here's the thing. We know that before the collision, we had a momentum of the car to the right, like so, and a momentum of the load like so, which means that the total momentum before is just the vector sum of those. And so here is what the total momentum looks like before the collision. But after the collision, everything, the car and the load, are moving together straight to the right. So here is P total prime. Now, you don't have to do any calculation to see that the initial P total and the final P total are not equal. And so momentum isn't being conserved here. We can see that without doing any further thought. But why? Why isn't momentum being conserved? Well, remember when momentum is conserved. Momentum is conserved when the system is isolated. And so let's think about what forces act on the car and on the load during the collision. So the car is, of course, going to have a weight. The load will too. The car is going to have a normal force up due to the tracks. The load is going to have a normal force up due to the car. The car is going to have a normal force down due to the load. And then additionally, the load has to get sped up to the right, right? It was initially going down. After the collision, it's going right. And so there must be some sort of a friction, probably kinetic. There's probably going to be some sliding around. Hard to say. Oh, Newton's third law tells us there's going to be a force back on the car that is also a friction. So just labeling all those. Here's the normal on the car. Here is the normal that the car exerts on the load and the normal that the load exerts on the car. The weight of the car, the weight of the load, the kinetic friction that the car exerts on the load, and the kinetic friction that the load exerts on the car. And we know that these two are an interaction pair, and these two are an interaction pair. Now we know that this system isn't isolated because its momentum isn't conserved. So the question now is why? Well, the system is not isolated if there are external forces that we can't ignore. So it can't be because of these normals that the load and the car exert on each other. Those are internal forces. And similarly, these frictions are internal forces. And so the only external forces we have to worry about are the weights and this normal force on the car. And let's just think about that, because if the momentum was conserved, then after the collision, the car and the load would be moving together diagonally down and to the right. Well, why don't they? Well, they don't because they don't burrow through the tracks. And so it should be a force due to the tracks, or in other words, this normal force acting on the car, that's the culprit. This is what's preventing the momentum from being conserved. Now, there could additionally be a rolling friction on the car, but as usual, those are pretty small. So what does that tell us? That tells us that momentum is not being conserved because of a vertical force. And that means delta P is vertical. And that means that while the vertical component of the momentum isn't being conserved, the horizontal component should be. So here's this vector nature of this all. So Py does not equal Py final. And so we can't really do anything with that, although we don't really care. We know what the vertical component of velocity is after. It's 0. However, because there are no horizontal forces causing momentum to not be conserved, the horizontal component of the momentum is conserved. And so now we can go ahead and work with that, because all we have initially, only the car is moving horizontally. And so we can say the initial horizontal momentum is m car v car. Simple as that. And then the final, they're moving together at speed capital V, and so it'll be m car plus m load, right, the total mass, times capital V. And so there we go. Capital V is just mc vc over the sum of the masses. And you can now work that out and get a number if you